My talk might be a little bit more technical than most, but I do have results at the end still. So I want to talk about CGS2 in the context of QR factorization and the Arnoldi process, and I want to thank Stephen, Kasha, and Julian for helping me with my research. This is going towards my PhD. So the contents, I'm going to go through motivation, context, and previous work, and then also we're going to go from CGS2 through QR and Arnoldi, moving from 3 syncs to 2 syncs to 1 sync, because I feel it's necessary to see that motion to understand the process of developing the Arnoldi 1 sync algorithm. So why CGS2? Well, it's stable enough, fast enough, it's faster than the level 1 implementation of modified Gram-Schmidt at least, and why do I care? Well, I'm interested in the orthogonalization schemes mostly, but they're needed for the Arnoldi expansion, for iterative eigenvalue solvers, as well as GMRes, and I'm also interested in the non-symmetric matrices. So the two contexts that we're focusing on again are QR and Arnoldi, where we delay the normalization for the first moving to 2 sync, and then delay that reorthogonalization so that we can achieve the 1 sync. And I do want to note that I am focused at one column at a time, so the S-step methods aren't exactly what I focused on. So the context. Inner products can be expensive. So they are large parallel distributed computation, and they require MPI all reduces. So there's essentially 3 phases within this computation, where phase 1 is where each processor can have their own individual computation, which is embarrassingly parallel. Phase 2 is point-to-point communication, which I assume to be scalable. But then there's the synchronization phase, or these MPI all reduces, which is a bottleneck and slow. So we want to remove these. But what I do want to know is that the potential gain that we can gain from moving CGS2 from 3 sync to 1 sync is only a factor of 3 here. So the previous work done, we have Hernandez, Roman, and Thomas in 2007, where they developed a CGS 1 sync, and we are going to be working and building upon that, and more importantly, we're adding contributions from Stephen's trick through QR and an Arnoldi trick that Julie and I had found together. So the building blocks, though, are building from Hernandez, Roman, and Thomas. So here we have the CGS2 algorithm in the context of QR. First projection are steps 1 and 2. Second projection, steps 3 and 4, standard R update and computing the norm. And then when we go to CGS2 and Arnoldi, you see it's the exact same, other than what we enter with. So we either enter in the next column A or the matrix vector product with the previous orthogonalized vector. So originally, when they're both 3 sync, the algorithms are identical, but when we actually start delaying these synchronizations, they do begin to differ. So let's start talking about QR from 3 sync to 2 sync. So the idea here is we want to take step 6 and push it onto the next iteration so that we can combine those synchronization costs, which forces us to move step 7. So the idea then is delaying this normalization by combining the synchronizations, and we usually would compute this matrix vector product with the next column of A, but now we have an unscaled column. So this is relatively easy because if you notice, all that this inner product hits is that last J-1 element from the inner product. So to be equivalent algorithms, it's actually not too bad. All we have to do is add step 5 and scale that last element. In the context of Arnoldi, though, it starts to be a little bit different, not too much right away. So it's the same game. We delay the norm. But we want to compute, again, Q transpose AQ. So now we have twice unorthogonalized vectors. So both uj-1 and auj-1 are unscaled. But that first inner product on the left, similar to QR, will only hit the last element. But the auj-1 hits every element. And because of that, we do a similar scaling. We add steps 4 and 5, where we scale each element from that inner product, but that last element twice. So moving from 3 sync to 2 sync is not too bad. But moving from 2 sync to 1 sync is where things get a little bit more tricky. So I'm going to show the algorithm first. So this is how we combine everything to 1 sync. And steps 2 and 3 are going to be the main differences that I want to try to explain, but I'm going to go over them pretty quickly because the Arnoldi is what I care about mostly. So delaying the norm as well as that second projection. So now we don't even have an unscaled column, we have an unscaled and once projected vector instead. So instead of computing what we did for going from 3-sync to 2-sync, we have to do this other inner product there. So like I said, we also need to do the second projection. So why do we do these two gem V's by themselves? Instead, we combine everything together and get optimized blast level 3 operations, which actually do improve performance as well. So the last thing that I should know is not only do we want to use compute the second projection, but we need to compute a norm as well, but with a once projected vector instead of the twice. So, but we don't want to incur another communication to compute the correct norm. So I don't know if anybody noticed on one of Stephen's slide, he had a theorem called the Rolling Stones theorem, and the idea is you can't always get what you want, so you just work with what you have. So that's kind of what our mind state is. So for this is to explain step 2. I'm just going to direct your attention to the bottom 2 equations there. And Ishii's talk yesterday kind of alluded on this and showed the algebra to like unroll that. So mathematically, that I minus QTQ would be 0. But because we're doing this numerically, it's not exactly 0. So after this, we drop that term, and it's essentially only an approximation. But the error that is produced by it is small enough to where it does not intervene that bad. So this down here is step 2 with the square root. And then the last step is to discuss how we come to with the step 3. And this is where we call Stephen's trick, actually. So Sj minus 1j, just the single element, is usually this inner product. So, and actually, once you unroll and use the definition of what Qj is, we can easily recapture this with what we do in One-Synch. So we compute Qj minus 2 transpose Wj minus 1, but we just take the transpose of that. That's these first 2 right here, which ends up being that T factor. And we already have the S1 through J minus 2 as well. So it's actually not too bad to catch up, which gives us the Stephen's trick and also the Pythagorean trick. So moving then from Arnoldi in the 2-sync sense to the 1-sync. So this is when things get a little bit tricky. This is our algorithm. So we have, again, the Pythagorean trick, Stephen's trick, and I'm trying to be kind of like clear to say, like, show the steps that are kind of consistent through each Arnoldi process. But we also have now this 9th step, which is the Arnoldi trick that I want to explain. So the biggest challenge is delaying the normalization, but delaying the second projection. So we compute this matrix vector product with that once unnormalized and once not projected vector. So the key idea that I want to emphasize is now we don't expand the Krylov basis through Q, but through W, the only once projected and unnormalized vector. But I want to be able to gain the numerical properties of CGS2 by reorthogonalizing, so we need to kind of capture this back. So again, the Rolling Stones, we do what we can and catch back up. So traditionally, again, we compute QTAQ, and but we do what we have, which is the Q appended with this unnormalized vector, unprojected vector. And again, we combine all of the computations together in a gem operation instead to get the level 3 blasts. So we don't want to incur that extra communication to compute the right norm. So this is where things get a little bit heavy. So I'm trying to be as clear as possible. So since we're expanding the Krylov basis through W, we need to guarantee we have the next Wj value before we exit that jth iteration. So the key idea that we have when we're moving forward is we can't afford any matrix vector products or any other inner products because those would be an additional communication. So what we do then is we kind of unroll and keep unrolling until we get something that works out, which actually is pretty nice. So we can't afford an AQJ minus 1. Well, we do compute AWJ minus 1, so we might as well use this within there. And if you notice, the only difference between the only issue is we don't have QJ minus 1 yet. So let's unroll just a little bit further. I'm going to copy and paste this up at the top. And the algebra, it's a lot. Again, just focus your attention. After we unroll, we can get this approximation term and drop out an entire portion, which becomes very useful. So after that fact, we have unrolled it into something of all these that we've computed. So in the context of our algorithm, I do want to say this S term is generated from the first projection. But the only issue now is we have a transpose here with AWJ minus 1. So this actually turns out to be Arnoldi's trick. So we're going to unroll this just a little bit further, and it comes out to something that we've computed completely with that One-Synch. So S, again, is the term associated with the first projection, and C is the term associated with the second projection. So the combination of these corrects doing that matrix vector product with an unnormalized and unorthogonalized vector. So now what I want to do is I want to take this and put it within the factorization form, because we're trying to rebuild up this representativity of these matrices. So what I do is instead of, I just reorder this so that AWJ minus 1 is over there, but we are almost there. We have Q, Q, and then W. So instead of unrolling the W that we compute up here, I take the QJ form, which is just the identity minus QTQ times that WJ, rearrange that around, and this is what we get. And I use this and plug it in there. And after that, with some algebra, I'm skipping a few steps because there's already been a lot, but we can get this in a form where we have AWJ minus 1 represented in the Krylov space basis of Q. But again, we seek the representation of AQJ minus 1 within this space. So we have to play this game just a little bit further. So here is how we define AQJ minus 1. And expanding it out, we see we have almost a representation of within the Q basis besides this, but we just spent all that work unrolling what AWJ minus 1 is. So now we can just input that and simplify it a little further, which is where we get this. So having this in this form immediately gives us the representation of what that Hessenberg matrix should be. So moving from here, you can see we have AQJ minus 1 appended, or with the representation. We automatically just take those inner products and put them right in that next column of the Hessenberg matrix. So again, this coloring scheme is me trying to be explicit so that we can kind of understand how these things are being unrolled. So the purple is because we have not normalized these vectors. We need to catch that up. The red are the standard reorthogonalization terms. The S, again, are just the first projection terms. This blue term is Stephen's trick exactly from the context of QR, delaying that orthogonalization. And then the gold up here at the top is from the Arnoldi trick. And this allows us to expand the Krylov basis through W, but then recapture it all within the Q basis, which gives us, again, this final algorithm that allows us to be One-Synch in a CGS2 framework. And then for numerical results, I do have, I've done a lot of numerical results, and I'm just going to give you some today, but we've done a lot through matrix market and specifically this one Manteuffel matrix. So first, our metrics for stability is we look at both the Arnoldi representativity as well as the orthogonality generated by those vectors. And then we also construct the Schur form of that Hessenberg matrix through LAPAC's DGEES and check the Arnoldi representativity of that along with its orthogonality. So that kind of gives us a little basis of Specifically with the manifold matrix, there's an explicit formula where we can check the eigenvalues. So we check the backward error, and we check this invariant subspace returned through DGES. And because of that, we want to see the level of that orthogonality ensure when we look at these eigenvalues that we check. So, and I do want to say for the sweet Sparse collection on Matrix Market that we use to test all of these, we've reduced the list from, I think we had well over 1,000 matrices originally, but we reduced it by the number of non-zeros because we wanted to be able to compute this in a reasonable amount of time. And some of those are really large. So this is the manifold matrix. It's just the sum of these two, where it's a convective diffusion model, and the H term is the discretization, and that beta term kind of governs the spectrum of the eigenvalues. So, and that's the formula to explicitly construct each eigenvalue for whatever size we decide. So it's a n block structure, so the total size is n squared. Okay, and now what I'm first going to present on is the 828 matrix market. So to give you a little premise, we have CGS, CGS2, CGS2, D is the delayed norm, and then the two DCGS2 algorithms. HRT stands for Hernandez, Roman, and Thomas, and then STAB is the stabilized version that we've worked on, and then the householder level 2 is the 5-sync that Homer Walker presented in his '89 paper about using householder in a GM-Res framework. So out of the 828 matrices, we can see the level of orthogonality, so we accept that if the Arnoldi representativity here is less than 10 to the minus 10, and similar with the orth, and we also use the tolerance that we set up here on the eigenvalues that we search for the Schur and orth, so we're using 10 to the minus 10 as well. So matrix market is funky. We can't explain all of the matrices that we use, so I can't fully explain why for some of them we don't get full representativity, but the orthogonality is what we really care about, and we do beat the other CGS2 methods for that. And that is what I care about, at least, because we don't want to keep reiterating on the same invariant subspace, and the orthogonality helps us with that. But as you can see, the invariant subspace that we find does beat all of the other CGS methods as well, but of course householder is the best. So, and this is not always consistent, because I'm going to show you results soon about the manifold matrix where actually householder doesn't do as well, and I can't explain that completely. So here's the manifold matrix. So I chose n to be 50, which means that the size of the matrix is 50 squared, so 2500. And what I do is I do Arnoldi full. So I have a restart at 100, and I increment by 100 until I get to 2500. So essentially, by the end of this, I've done like a Schur decomposition, so I would hope that I would get a full invariant subspace of this matrix. And as you can see, this dotted line would be if we had that full at each iteration, but we don't get there until the end. And most schemes actually do appear to be pretty similar. But here, I can't explain why householder bounces around a lot less with manifold. So all that information condensed into this plot, or the table. And so from 100 to 2500, that's 25 incrementing by 100, so that's where that comes from. And all methods do pretty well, except for, of course, HRT. And that's because of the size of the restart. They don't, their method seems to fail if you do higher than a 50. Restart of 50. But DCGS2 here beats out every other method, which is good to me. Finally, the last plot I want to talk about is, so this was done on 128 processors with a restart of 70, and I really like this plot. So we vary the matrix size on the x-axis, and the y-axis is the number of grid cells per second that we actually compute. So you would expect this to be a solid, like a flat line, but as the matrix size increases, of course, we don't see this. So there's two things that I want to emphasize here. This line right here, this data point, is where you actually see the synchronization, the cost of the communication. So we have householder 5-sync, 3-sync, 2-sync, and One-Synch. So that's pretty clear. But as the size of the matrices increase, the flop demand increases. So then the communication becomes less important, but the flops do. And our method is that much, it's better than the others only because we combine the two GEM-Vs into the GEM operations to get that increased performance. So then my conclusion is, so we have developed the CGS2 in the context of Arnoldi, and we have it in the context of QR, and I'm working on a householder One-Synch right now. I have a Two-Synch already, reduced his Walker's 5-sync down to 2, and I just want to play this game again then with the householder to move it down to a One-Synch. And as well, I'm working on the stability analysis of this for both QR and Arnoldi. Thank you.